talk in this FDP. So, the topic for today's discussion is the small footprint automatic speech recognition free keyword spotting. So, uh, before I start with the actual content of the today's talk, so let's have a quick overview of what is the keyword spotting, basic concept of keyword spotting, and why do we require this in our practical life. So all of us, in fact, are using the keyword spotting, maybe knowingly or unknowingly in our day-to-day life. For example, when we say, hey Alexa, or let's say, hey Siri, okay Google, okay. So all of these are the simple examples of keyword spotting. So when our mobile phones are switched on, okay, so all the time we are having some audio activity, but amongst all the input audio signal, the Siri or Alexa or Google is wake up only when we say, let's say Alexa, or let's say Google or Siri. So all of these act as a keyword, and what enables the triggering task is the simple algorithm of keyword spotting. So in a way, all of us are familiar with the keyword spotting, but what we are going to see over next few minutes is the special case of keyword spotting where we do not want the speech recognition that enables the keyword spotting. So what we want is a speech recognition free keyword spotting, and also we want it to be employed on the edge devices. So we want it to be as small memory consuming, as small computationally expensive as possible. So this is the basic, you can say, objective of today's talk. So I'm Dr. Himanshu Padole, working as assistant professor in IIT Bhubaneswar. And this is basically the work done by my MTech student Vijay Das. So coming to the contents. So first, I'll try to introduce the basic concept of keyword spotting, followed by the precise problem that we want to solve here. Then comes the proposed keyword spotting model, where I'll be discussing the 4 keyword spotting models that are proposed in this work, followed by its experimental verification and results on the standard data sets. We'll also compare the results of our proposed algorithms with that of the existing one. Finally, we'll have some ablation study to get the best out of our proposed models. And finally, we'll conclude the work along with our pointers for the improvement of the proposed models. So coming to the formal introduction of keyword spotting. So in any keyword spotting, the ultimate goal is to find a particular term in the incoming voice stream. Generally, the voice stream is continuous, and in that continuous voice stream, we want to spot a specific word. For example, it may be Alexa or Google or Siri or anything. So uh, the main task of the keyword spotting is to identify that target keywords. And that then can be used to trigger the predefined downstream task. So when it comes to applications of keyword spotting, it's commonly used in all smart home devices, then in-car voice assistants, then voice-enabled interactive voice response, wearable devices like smartwatches, gaming, and so on. So all of us are familiar with the applications of keyword spotting, but what we'll be seeing now is an algorithm that enables its deployment on a small edge devices, and which can work in a language agnostic environment. Yeah. So when it comes to general concept of keyword spotting, it can be categorized into one of the two basic main approaches. The first is automatic speech recognition, that is ASR based approach. The second is automatic speech recognition pre approach, which is called also as ASR pre approach. So as the name suggests, in the first approach, the very first task before the actual keyword spotting is the speech recognition. So when it comes to ASR based approach, we first try to recognize what is there in the incoming voice stream. So first task is basically the translation of the incoming audio into text. And once we have the text, then the detection of a keyword is a trivial task, because when it comes to the text, it is as simple as running the Control F command kind of thing. So in the ASR based keyword spotting, the main challenge is the speech recognition. And when it comes to speech recognition, as all of us in the era of natural language processing are very familiar with the large advanced neural network architectures, which uh, make use of transformers, attention models, and so on. So when it comes to ASR based approach, often all of these architectures employ these large advanced neural network architectures, which are computationally expensive and also requires large language data sets. So basically, these poses a limitation on their application for the edge devices. And also, because it's speech recognition based approach, so inherently it becomes language specific. So let's say when it comes to local languages, for which the large language data sets are not there, basically the labeled data sets are not there, then such models often perform poorly. Of course, they are very good on the languages like English, but for the local languages, their performance is often questionable. Now, the solution to this is the ASR free approach. So, in ASR free, we try to detect a keyword directly using the audio signal without recognizing the content of the audio. So, what we try to do is basically we try to do some sort of template matching where the actual audio waveform is compared with the waveform corresponding to the predefined keyword. So, in this approach, we only make use of the audio characteristic, not the meaning of the incoming voice stream. So this is called ASR free approach, because we are not actually recognizing the speech and then spotting the keyword. So obviously it becomes computationally less expensive, and also the memory requirements are on a lower side. And the main advantage for this kind of approach is that because we are not detecting the content of the audio stream, so it makes it inherently language independent. So this is the main advantage when it comes to ASR free approach. So with this background, in this work, we are focusing our attention on the ASR free algorithm development. So when it comes to ASR free approaches, with the recent rise in the deep learning architectures, many approaches have been proposed for the keyword spotting using the recent deep learning models, starting from the basic CNN or deep neural network to a more recent models that employ the keyword transformer, or let's say resonate or attention module. And very recently, last year, the swing transformer has also been employed for the ASR free keyword spotting. And as we can see, with the more advanced deep learning architectures like swing transformer, the accuracies have reached up to a very high level of around 98%. So as we can see in the table, very recently, the accuracies have reached the level up to 98%, but if we go through the table, the higher accuracies comes often with the more complex deep learning architecture. For example, the last paper uses the swing transformer. And once we go for the architectures like transformers or LSTMs or attention model, all of them come with the increase in the training time, run time, the memory requirements, and the computational resources. So, although the accuracies can be increased by using the more recent and advanced complex deep learning architectures, it poses limitation on their application in the resource constrained environments like edge devices. For example, if we want to deploy such algorithms for say wake up word detection, where we want to scan the incoming audio 24/7. So these algorithms often consume the large power, which is not desired. So this makes it challenging for its application, real-time application in low resource environments. For example, keyword spotting in, let's say, our smartwatches, which have very small battery. So what we aim here is to design an efficient ASR-free KWS model. And when we say ASR-free, it's inherently language independent. And when we say efficient, we imply a lightweight algorithm which has a low computational complexity, minimum training parameters that would make it feasible for deployment in small footprint edge devices. So this is the objective that we want to deliver in this particular work. Yeah. So now to solve our proposed objective, we suggest here the four.
Sir, you are presenting
Yeah.
something? Hello?
Yeah.
So you
Yeah.
are presenting something?
Yeah, I am presenting.
Sir, not visible, sir, actually. You are not shared yet. No.
Okay, sorry. Now is it visible?
Yes, sir, visible, sir. Sir, can you explain from starting if it's possible?
Yeah. Okay. Okay. You could have said it earlier. Sorry. I didn't know it was not shared. Okay. Now I think it's visible.
Yes, sir, visible, sir.
Yeah. Yeah. So most of the initial contents, I think, do not require the text, but whatever is required, I'll repeat it again. So the main objective here is the small footprint automatic speech recognition pre-keyword spotting. So as discussed earlier, the keyword spotting is a task where we want to find a particular term in the incoming voice stream. Okay, so mostly the voice stream is continuous, and in that continuous voice stream, we want to recognize where a particular target keyword appears, if it appears. So the common use cases for this is in our smart home devices like Google Home or Alexa, where we trigger the task using the specific terms like, let's say, Hey Siri, OK Google, Hey Alexa, and so on. Then there are other applications like smartwatches, wearable devices, then voice enabled interactive voice response. So all of these smart gadgets make use of the keyword spotting, and we are very familiar with all these applications. So while applications of these are very clear, when it comes to methods for the keyword spotting, there are mainly two approaches. The first is ASR based approach, where ASR stands for automatic speech recognition, while the other is ASR free approach. So as the name suggests, the ASR based approach make use of speech recognition for the keyword spotting. So what it does basically is, first it recognizes the speech from the incoming audio, where it basically tries to translate the incoming audio into the text. And once we have the text for the incoming audio, the keyword spotting task is quite trivial. It's like a control F command in the PDF. Once we have a text, finding a particular word is quite trivial task. So main task in the ASR based approach is the speech recognition task. So, and when it comes to speech recognition, often all the speech recognition methods employ huge neural network architectures, uh, which involves attention mechanism or LSTM or transformers and so on. And they essentially require large computational resources and the training on the large language datasets. So another limitation of the ASR based approach is that because it involves the speech recognition, so inherently it becomes language specific. It works for a given language and the same algorithm doesn't work for another language. So it makes its use limited for a given language on which it is trained. So quite often, most of the ASR based approaches works well on the rich languages like English, for which a large training is available, but they perform poorly on a local languages for which the labeled training data is quite sparse. So a solution to this limitation of ASR based approach is the other approach, which is ASR free approach. So when it comes to ASR free, as clear from its name, it doesn't require the speech recognition for the keyword spotting. So what it does is that it directly works on the audio characteristic of the incoming audio signal. So basically it tries to do some sort of template matching in which the template or the audio waveform of the required keyword is compared with the incoming audio. So wherever it matches to a large extent, we say that keyword is spotted, otherwise not. So this approach doesn't depend on the language because it directly works on the waveforms of the audio. So inherently it becomes language independent because it doesn't require the speech recognition, and also because it tries to do some sort of a simple template matching, it also reduces the computational burden and memory requirements of the algorithms. So this basically enables its deployment on a low resource environments like edge devices, which is the primary goal of our proposed work. So with this motivation, in this work, we focus our attention on the ASR free approaches for the keyword spotting. So before we start describing the proposed models, we first will have a brief overview of what has been done in the domain of ASR free keyword spotting. So with the recent rise in the deep neural network architectures, most of the recent neural networks have been employed for the task of ASR free keyword spotting, starting from the basic CNN and deep neural network to a more recent architectures like Resonate or Transformer or attention based models. So as we can see, with the more and more complex architectures, the accuracies in the keyword spotting are consistently increasing. So as we can see in the last paper, a more recent paper in 2024, with the use of Swin transformer, the accuracies in keyword spotting have reached up to very high level of 98%. So although the accuracies have reached up to very high level of, let's say, 98%. All of these architectures, if we go back to this, okay, are employing some of the very advanced neural network architectures like swing transformer or LSTM or ResNet and so on. So when it comes to deployment of such architectures, they come with the large training time, runtime, the large memory requirement, and obviously the computational resources. So although the accuracies have reached to very high levels, all of these algorithms come with the memory and the computational requirements, which are not very feasible when it comes to small footprint devices, like let's say very small smartwatch, which has very limited memory and the computational resources. So in this particular work, we aim to provide a solution that is ASR free, which makes it inherently language independent, but also at the same time a lightweight with very limited computational and memory requirement. So what we try to achieve is keyword spotting algorithm which uh, which has a reasonable accuracy, but when it comes to computational complexity and the memory, it is very it's feasible for the deployment on the small footprint devices like edge devices. So uh, this sets the stage for what we are going to see now. Yeah. So with this objective of designing the efficient ASR-free AWS model, which is lightweight in terms of computational complexity and the memory, we are proposing here the four different AWS model, starting with a more traditional approach that uses the MFCC and the CNN for keyword spotting, followed by the univariate time series classification based KWS model, wherein for the first time we are making use of time series classification for the keyword spotting. Third is the multivariate extension of the UTSC based KWS model, where we are making use of multivariate time series classification for the KWS task, and followed by the and followed by it is our final model, which integrates the multiple features in the multivariate time series classification models. So I'll be going through each of these one by one. Yeah. So starting with the most basic MFCC and CNN based AWS model. So what we do here is a more conventional approach where we take the raw audio data, a small segments of raw audio data, typically of the size 1 second, and divide it into overlapping frames where the window size was set to be 25 millisecond and hop size was taken as 10 millisecond. Why do we choose only the window of 25 millisecond and hop of 10 millisecond will be clear when we go to the ablation study. But right now, let's say we have a or raw audio file of 1 second, which we have divided into overlapping time frames with window size of 25 millisecond and hop size of 10 millisecond. So once we have the overlapping time frames, what we do next is we extract the MFCC representation from each of these overlapping windows. So once the MFCC features are extracted, this results in a 2D matrix of dimension 13 cross 99, where 13 is the number of MFCC coefficients in each overlapping window, and 99 is the number of total overlapping time frames. So this makes a 2D matrix of dimension 13 cross 99, which can be seen here. Yeah. Now, once we have generated the MFCC representation from the incoming 1D audio data, this MFCC is then treated as a 2D matrix, very similar to an image of dimension 13 cross 99. And when it comes to the classification of 2D images, CNNs are typically well suited for handling such 2D nature of the input. So, exploiting that property of convolutional neural network, we provide this MFCC representation as an input to a CNN with the architecture shown here. And this CNN is then learned, the weights are learned to classify the incoming audio into 12 classes, where what are the 12 classes will be clear when we discuss the data set and experimentation part. So basically 12 classes yeah. So these 10 keywords form the 10 classes of the classifier, and the additional 2 classes are the silence and unknown. So together these 10 keywords, then silence and unknown, makes it a 12 class classification problem. We'll discuss this in more detail once we go to the experimentation part. Yeah. So coming back to our first model, MFCC and CNN based model. So this MFCC representation is treated as a 2D image, which is then provided to a CNN that classifies the incoming image into one of the 12 classes, which corresponds to the 10 keywords and the silence and the unknown class. So these are the details of the CNN configuration. And on the Google speech command dataset that we have used for testing all our proposed model and the existing state-of-the-art models, with 150 epochs, we have got the accuracy level up to 91.7%. So although it's quite although conceptually the MFCC and CNN based model is quite simple, the accuracy level are promising, with the accuracies going up to 91.7%. But what happens when in case of the MFCC and CNN based approach is that because we are treating this MFCC representation as a 2D image, we are neglecting the temporal evolution of the MFCC coefficients, which is inherently present in the time evolving audio data. So because our data is audio data is temporally evolving, all these MFCC coefficients are also evolving over time. But for a CNN, the input is a 2D image, where this evolution, temporal evolution of MFCC coefficients is neglected. So although it's giving accuracies, promising accuracies with the classification accuracy up to 91.7%, it's inherently losing the information which is there in the temporal evolution of the MFCC coefficients. So what we propose next is a model that can exploit the temporal evolution of the incoming audio data. So with this in mind, what we propose next is the univariate time series classification based KWS model, wherein for the first time we are proposing the use of time series classifiers for the keyword spotting task. So as we can see, the incoming audio signal is a sequential data, which is basically a one-dimensional time series. So when it comes to keyword spotting, basically we are interested in classifying the one-dimensional time series. So the problem of keyword spotting can be formulated as a univariate time series classification task. So here for the first time, we are making use of time series classifiers for the keyword spotting application. So what we do here is that from the raw audio data, we are first extracting the univariate time series features, which are then provided to different standard classifiers like SVM, logistic regressions, ridge regression, and so on. So this approach essentially exploits the temporal information present in the audio data, which was not exploited in case of the earlier model, that was MFCC CNN based model. So this is the performance of the proposed UTSC based model for different time series feature extractors. So amongst the different state-of-the-art time series feature extractors, the Rocket and the RDST feature extractors perform the best with accuracy levels of around 78%. Now, as compared to the earlier model, as we can see earlier, the accuracy level was around 92%. Now it comes down to 78%. So why this happens is that as compared to the previous approach, what is lagging here is that we are directly working on the raw time series data. Whereas in the earlier case, we first extracted the MFCC coefficients from the raw audio signal. So although in the second model, we are exploiting the temporal evolution of the data, we are not able to capture the acoustic features of the audio data, because as compared to any other temporal sequence, the audio data has some very specific characteristics that can be captured through the MFCC coefficients. So this is the reason why, although we are here able to capture the temporal evolution, the accuracy levels have dropped from 92% to 78%. So to combine the advantages of both the MFCC based approach and the time series based approach, what we propose next is the extension of the univariate time series classification based approach, which works on the MFCC representation rather than the simple raw audio time series. And that forms our third proposed model, which is named as multivariate time series classification based KWS model. So what this third model does is essentially it combines both the acoustic information in the form of MFCC coefficients and also captures the time series specific information through the multivariate time series classifier. So similar to the first model, the raw audio data is first transformed into MFCC representation, which is again a 13 cross 99 dimensional matrix. But now, unlike the first approach, wherein we treated this 13 cross 99 matrix as a 2D image, here we model this 13 cross 99 dimensional data as a multivariate time series of dimension 13 and length 99. And why we do here is that the reason is because these MFCC coefficients are computed for each of the overlapping windows which are evolving over time. So if we look at this matrix of dimension 13 cross 99, each of the 13 dimensional vector is computed over a consecutive time frames. So basically it can be treated as evolution of these 13 coefficients over the time. which makes it a 13-dimensional time series. So with this representation, we formulate now the problem as a problem of keyword spotting as a multivariate time series classification problem, where the input is a 13-dimensional time series, which is basically the time series representation of the MFCC coefficients, and then we employ various multivariate time series feature extractors and classifier to do this multivariate time series classification task, very similar to what we have done in case of the univariate time series classification based model. So now compared with the last model, it's very similar except for the fact that here we are making use of multivariate time series classifier, and instead of the raw audio data as an input to time series classifier, we are applying the MFCC representation, which is basically a multidimensional time series of the MFCC coefficients as an input to multivariate time series classifier. So now this model for the first time extracts both the temporal and the acoustic features of the incoming audio. So as expected, it performs better than both the individual models, and the same is verified in the results shown here. So now if you compare the results of the MTSC algorithm, different MTSC algorithms, the RDST model outperforms both the MFCC CNN based model and the univariate time series classification based model, with the accuracies going up to 93.6%. And this essentially verifies the utility of the multivariate time series classification based approach, which exploits or which combines the strengths of both the acoustic features along with the time series specific features. And this is for the first time any KWS model is exploiting both the acoustic features and the temporal features. So now, although this MTSC based KWS model is providing the accuracies better than both the MFCC and the UTSC based models, the accuracies are still not as good as the existing state-of-the-art models. And the reason is here we have not fine-tuned that feature extraction process. Basically, in this model, we have employed the default time series feature extractors, which are not specifically tailored for our proposed KWS application. So what we do next is we try to improve upon the time series feature extraction, which ultimately results in a better classification accuracy. So as we can see on the right hand side, that again for this model also the Rocket and RDST performs the best. So we try to fine tune both this Rocket and the RDST algorithms further, which are discussed next. Yeah. So because in all the results that we can see, consistently the Rocket and RDST are the two top performing time series feature extractors. So for the further analysis, we focused our attention to these two time series feature extractors, namely the Rocket and the RDST. So Rocket is a random convolutional kernel transform, while the RDST stands for the random dilated shapelet transform. So these are two recently proposed time series classifiers. So as we'll be fine tuning these two to improve the accuracy of the KWS model. So I'll briefly go through the basic working mechanism of Rocket and RDST that will enable us to understand how they can be further tuned to improve the overall accuracy of the time series of the keyword spotter. So when it comes to rocket, it's basically very similar to how a CNN acts, but with two major differences. The first, okay, before I go into details, the figure 7 represents the basic processing pipeline of a rocket algorithm. So what it does is that for a given time series, the time series is convolved with random wordy kernels. So each of that uh, is then passed through two pooling operations, which are the max pooling and the PPV, which stands for proportionate positive values. So each of the kernel basically results in two summary values. One is the max value, the other is PPV value. So essentially for k kernels, it results in a set of 2k length vector. So as can be seen in the figure, if we are using k number of kernels, we are ultimately getting a feature vector of length 2k. And then this feature vector is provided by default to a rich classifier. But here we have also tried different classifiers like logistic regression or random forest, SVM, and so on. So this is the basic working principle of the rocket classifier. So its working is quite similar to CNN, but with two major differences. The first is the kernel weights, unlike the CNN, are not learned here. So here the kernel weights are randomly chosen from the normal distribution of mean 0 and standard deviation of 1. So the kernel weights are randomly assigned, unlike the CNN where the kernel weights are learned. And the second major difference is that there is only one convolution layer, not the multiple layers of convolution. So these are the two major differences as compared to a standard convolutional neural network. But essentially, it is some sort of convolutional algorithm, very similar to CNN. Yeah. Now, the second algorithm that consistently performed well was the RDST among compared here. So when it comes to RDST, which is a random dilated shapelet transform, what it does basically is that uh, it first selects some of the shapelets, a predefined number of shapelets from the given time series, and then try to find in the and then for a given time series, it tried to find the minimum distance of the small, you can see through a figure, it's simpler. So what it does is that for a given shapelet candidates, it slides over all the finite length subsequences of the given time series and then tries to find the minimal distance, then its location and the threshold based frequency. So basically for the k number of shapelets, it results in a 3k number of features. So where the first is the minimum distance, second is the location, and third is the frequency of occurrence. So with this brief overview of two time series feature extractors that we have used extensively in our work. I think now we can discuss the next part in the MTSC based KWS model. So as seen earlier, the main parameters that decide the feature extraction are the number of kernels in Rocket and the number of shapelets in RDST. So as expected intuitively, as we increase the number of kernels and shapelets in Rocket and RDST respectively, we should get richer features, and the richer feature should result in the increased classification accuracy. To verify this intuition, we perform experimentation using different number of kernels in Rocket and different number of shapelets in RDST, the results of which are shown here. All of these results were obtained on Google Speech Command Dataset version. So as we can see, as expected, when we are increasing the number of kernels in Rocket from the default value of 10,000 all the way up to 120,000, the accuracy level increases from 89.8% to 95%. Similarly, for RDST, when we are increasing the number of shapelets from the default value of 10,000 to the value of 50,000, the accuracy reaches the maxima of 95.1%. So this essentially highlights the importance of choosing the appropriate number of kernels or shapelets in the feature extraction part here. Yeah. So before we discuss the results in details, I'll give you the brief overview of data sets used in this entire analysis. So as briefly mentioned before, all these initial results are obtained on the Google Speech Command version 1, which is basically a data set containing 1 second audio snippets sampled at 16 kilohertz, while version 2 consists of 1,05,000 samples of 35 distinct words, and version 1 consists of 65,000 samples of 30 words. In this particular work, we have used the 10 command words out of all the 30 words, which are up, down, left, right, yes, no, on, off, go, and stop. So these 10 command words were chosen as the target keywords. The remaining words formed the unknown class, and the last 12th class was the silence class, where no particular speech was present in the incoming audio. Similarly, to verify the generalizability of the proposed model, we evaluated its performance on one more dataset, publicly available dataset, which is free spoken digit dataset. It consists of 3,000 audio samples, which basically is the audio corresponding to digits from 0 to 9. All of these are recorded at 8 kilohertz, and again, each is having a length of 1 second. Now, similar to earlier analysis, here also we introduced 2 additional classes of unknown and silence. Yeah. So, with this brief introduction or brief overview of the datasets used, now coming back to the performance of the proposed model on the GSC version 1, as we can see in this table, when we are increasing the number of kernels from 10,000 to 120,000, the accuracy is increasing from roughly 90% to 95%, which is desired. Similarly, for RDST, when we are increasing the number of chiplets from 10,000 to 50,000, the accuracy is increasing from 93.6 to 95.1%, which is also a desired phenomena. But this increase in the accuracy also increases the number of features involved in the training of the KWS model. So specifically, when we are having the number of kernels in the rocket as 120,000, for each of the kernel, it gives two values, the max value and the PP value. So for 120K kernels, it results in 240K number of features for rocket. Similarly, when it comes to RDST, each of the shapelets gives rise to 3 features. So 50K shapelets results in 150K number of features for the RDST. And now each of these feature vector, as can be seen in this, each of these feature vector is provided to a 12 class classifier. So when it comes to, let's say, reach regressor or logistic regressor, this feature vector is provided to a 12 class classifier, which essentially results in total trainable parameters as 12 into whatever is the feature length, which is 240K in case of rocket and 150K in case of RDST. So this roughly results in the total trainable parameters of 2.88 million for the rocket-based MTSC classifier and equal to 1.8 million for the RDST-based keyword spotting algorithm. So although with this increased number of kernels or the increased number of shapelets in rocket and RDST respectively, we have achieved the higher accuracies of around 95%. It also increased our memory requirement of the algorithm, which and this defeats the purpose with which we started all this analysis. What we wanted, if we go back to our original objective, what we wanted was an algorithm with reasonable accuracies, but which has a very limited computational and the memory requirement so that it can be deployed on the edge devices. So with this increase in the number of kernels and shapelets, the number of parameters is also rising to a very large value of 2.88 million and 1.8 million respectively. So now this essentially restricts the applicability of the proposed model in the resource constrained environment, which was the basic objective of our proposed KWS models. So to circumvent this, what we do next is we try to somehow reduce the dimensionality of the feature using different dimensionality reduction method, wherein specifically we employ the principal component analysis after the feature vector is extracted. So what we do here is now, as compared to original model, after the feature vector is extracted, a PCA block is introduced, which essentially reduces the dimension of this original feature vector. This table shows the result of the dimensionality reduction on the effect of the dimensionality reduction on the classification accuracies. So now, as we can see, if we try to reduce the number of features for a rocket from 240K to here, the first row corresponds to 20K, the accuracy is brought down from 95% to around 94.8%. So for a 12 times reduction in the number of parameters, the drop in accuracy is roughly around only 0.2%. And this provides a reasonable trade-off with a 12-time reduction, the drop in accuracy is roughly around only 0.2%. Similarly, when it comes to RDST, when feature are reduced from the original 150K to a very small number of 5,000, the accuracy is brought down from the original 95% to a reduced value of 93.36%. So although the accuracy is roughly brought down by 2%, the reduction in number of parameters is almost 30 times. So what it shows essentially is that to enable the deployment of the proposed models on a small footprint devices like edge devices, we can have this feature reduction using PCA and still retain the classification performance intact to a very close value to the original value. Just a minute. Yeah. So having verified the efficacy of both this rocket-based MTSC model and the RDST-based MTSC model with the reduced feature size, what we propose next is once we know that both of these rocket and the RDST-based models are performing well individually, what we think next is the combination of both, because the rocket-based algorithm essentially extracts the convolution-based information, whereas the RDST essentially extracts the shapelet-based information. So when both of these methods are extracting the distinct information, what we try to do next is to combine or to fuse the information from both of these time series feature extractors. So essentially, the upper part of this model exploits the information using the rocket feature extractor. The lower part exploits or extracts the information using the RDST feature extractor. So after the feature reduction, dimensionality reduction using PCA, here the 20K length feature obtained using rocket is concatenated with the 5K length feature obtained using RDST. So essentially it results in a combined feature of length 25K, which is then provided to a classifier, which are again either the reach or logistic or random forest and SVM and so on. So all of these are discussed in detail in the results section. Now, as expected, when we are combining the features using both the rocket and the RDST, the resulting accuracy is better than their individual accuracies. So as we can see, for a 20K length rocket feature, when concatenated with a 5K length RDST feature, the accuracy again increases to the original level of around 95%, which slightly lower than it, it's 94.95%. But what it verifies is that with this integration of the distinct time series feature extractors, we are able to surpass the performance of their individual model. So with this feature fusion, the number of parameters increases slightly and it goes to a value of 300,000 as compared to the rocket-based approach, which had the number of parameters equal to 240K. But it also increased the accuracy to almost the original level of 95%. Yeah. Now, all of these results that we discussed so far were obtained using the Google speech command version 1. Now, to attest to the generalizability of the proposed KWS models, we evaluated its performance on two more data sets, namely the Google Speech Command version 2 and the free spoken digit dataset. So this is the result obtained on the Google Speech Command version 2. So here also we can see, as expected, the integrated model performed the best as compared to the original individual models, and the accuracy was reasonably high with level up to 94%. Similarly, we compared its performance on the free spoken digit dataset. So here also a same trend was observed where the integrated model combining the RDST and Rocket performed the best with the accuracies reaching up to the level of 98.8%. So this is even better than the accuracies obtained on the Google Speech Command dataset. Now, to have a fair comparison of our proposed KWS models with that of the existing state-of-the-art methods, we compared the accuracies of our proposed models with all the existing state-of-the-art KWS models as discussed earlier. So we can see here that except for the third except for the transformer based models with number 3 and number 7, our proposed models are performing better than most of the existing state of the art ASR-free KWS models. But this keyword transformer based model and the swing transformer based models are having the accuracies higher as compared to our proposed model, with accuracies reaching up to 98%. But the catch here is that if we try to compare the number of parameters that are used in these two models, okay, so this graph compares the accuracy and the number of parameters used by the models simultaneously. So as we can see in this graph, both these transformer based models are using the number of parameters which are higher than 3 million. These are in the ranges of 3 million and 5 million respectively. Whereas the number of parameters for our proposed keyword spotting models are in the range of 300 K. So there is almost the difference of 10 to 15 times when it compares when we compare the number of parameters, whereas the reduction in accuracy is only around 3%. So when it comes to a trade-off of classification accuracy and the memory requirement, obviously our proposed models are superior as compared to the existing transformer based models, which was the original objective of our entire work presented here. Now coming to the last part. So as discussed initially, when it comes to the feature representation using MFCC, the size of window length and hop size is very important. So to select the optimal, to obtain the optimal MFCC representation, we tried different window length and hop size as shown in the graph here. So as we can see, the highest accuracy was obtained for the window length of 25 millisecond and the hop size of 10 millisecond, and hence was chosen to obtain the MFCC matrix. Now coming to the next part in the MFCC representation, the MFCC we tried with both 13 coefficients and 39 coefficients. We also tried another representation using spectrogram. And amongst all, the MFCC with 13 coefficients was found to provide the best classification accuracy of value 94.94%. And that's why when it comes to the MTSC representation, we have gone with the 13 length MFCC coefficient and the hop size of 10 millisecond, window length of 25 millisecond. This is the calculation showing why with the 25 millisecond window and 10 millisecond hop size, the number of frames come out to be 99. And finally, the last block in our model, which is a classifier. So as expected, as we change the classifier, the classification accuracies are also changing. So we tried using different classifiers like Ridge classifier, logistic regression, support vector classifier, and the random forest. So amongst all, the Ridge classifier consistently performed better, and hence we selected the Ridge as the classifier in all our proposed KWS models. So whenever we have shown the classifier block in all the proposed models, the Ridge was performing the best. And closely followed by the logistic regression. Yeah. So coming to the conclusion part, so in this work, we uniquely formulated the KWS problem as the time series classification task, firstly as a univariate time series classification, and then extended it to a multivariate time series classification task. So the univariate time series based model for the first time formulated the KWS task as the time series classification task and considered the temporal evolution of the speech signal, incoming speech signal, while the multivariate time series classification based approach uniquely exploited both the acoustic features like MFCC and the temporal evolution of the audio signal. So this is for the first time any KWS model is simultaneously exploiting both the acoustic and the temporal features of the audio signal. And this integration of acoustic and the temporal information resulted in a state-of-the-art accuracy of around 95% when the number of parameters are also considered. So with a small number of parameters in the range of 300K, we are achieving an impressive accuracy of around 95%. So overall, the proposed KWS models present themselves as a good alternative for a small footprint language agnostic ASR-free keyword spotting, which can be deployed in low resource environments like edge devices, which have very limited computation power and the memory. So of course, with all these advantages, there are some limitations of the proposed models. So herein, we have only utilized the MFCC and spectrograms for the acoustic feature extraction. But there are other advanced time frequency representations also, which are not yet exploited in our work. Further, when it comes to dimensionality reduction, we have gone only with the PCA. Whereas recently there are more sophisticated compression algorithms like encoder, decoder, autoencoder. So these algorithms can also be exploited, which may result in a more sophisticated models with the improved accuracy. So these are some of the references. I think that's all from my side. I'm open to the questions from the audience. Thank you for listening to me patiently. Yeah. So, uh, if you have any questions, you are most welcome. Am I audible?
Yes, sir.
Yeah. So, in audience, if you have any questions, you are most welcome. You can ask it.
Sir, please write your email in the chat box so participant can contact you if you have any questions.
Okay. Yeah. Someone asked the question, Rekha DIP. You can
Sir,
unmute and ask.
question from Suman Rekha Deep, sir.
Yeah. So she can ask. Maybe you can unmute her.
Hello, sir.
Maybe you can unmute her.
Actually, sir, there is no rule to unmute to participants, sir. We can
Okay. So
they
she
can
cannot
they
ask.
can communicate through chat only. Participant.
Okay. Okay. So how will I get to know what is her question?
Question is I have regarding your based on Alzheimer disease.
Yeah, that is fine. But the question, specific question, she has not asked.
Have you seen the question, sir, from Suman?
Yeah, yeah. I'm writing the reply.
Sir, you can reply through video, audio.
Okay, okay. Yeah. So Rekha,
So ma'am,
you can just email to me regarding this abide dataset. I'll connect you with my PhD student who has recently used and worked on the abide dataset. So maybe you can contact him and you may get some help from him. You can just drop an email to me. Uh, any other queries? So if you have any queries, you can always email to me. I have shared my email ID with all of you. If you have any queries right now, you can message in the chat box. Sir, I think there are no more questions right now. So,
okay, sir.
yeah.
At the moment, Hema sir is not here, so sir, you can leave.
Okay. Okay. Thank you.
I can inform him. Okay, sir.
Yeah. Yeah.
Okay, thank you, sir.
Yeah. Wait.